Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to MOOC course on applications of interactomics using genomics and proteomics technologies. Today's lecture will be delivered by Dr. Uma Sinha Datta. She is a global training manager at GE Healthcare. Dr. Uma's research experience includes molecular virology, molecular and structural characterization of segmented RNA virus, early detection kit, both for immunodiagnostics and RT-PCR. She is an expert in surface plasmon resonance technology, especially GE's BioCore certified trainer, and in cell analyzer GE's high content analyzer. In the next two lectures, Dr. Uma will explain the concept of surface plasmon resonance technology by using BioCore technology platform. She is going to provide you not only basic understanding of how SPR works and how the BioCore technology platform works, but also a brief overview of applications possible and how to process the data, analyze data and interpret in meaningful manner. So, let us have Dr. Uma Datta Sinha's lecture today.
So, you all had a chance to look at the BioCore. We talked about some of the SPR technologies, how it actually determines the interaction based on the surface plasmon resonance technology, right. You know what's the association phase, what's the dissociation phase, regenerations required, right, to run the cycles. So, post that, I would like to talk about a little bit on the assay development part. When you are ready to do your or start up with your BioCore experiments, what are the things that you would like to take care, when you have two interactants and you would like to see the interactions, what are the things that you would like to optimize, which one should go as a ligand, which one should go as an analyte, various other things, what would be the reference service like, things like that. So, let us start. So, this is the basic assay development. Before I do that, I would like to spend a minute to talk about the organization that I work for. So, I am part of GE Healthcare and I work for a small group called Fast Track. Fast Track is actually a group which offers services to the customers. There are two parts to it. First is the process development, the other is the training and education. And I am currently the global Fast Track training manager. So, I take care of all the trainings that happen globally. And Fast Track, like I said, it is a global organization. It is located strategically over the world, and we do all kinds of process developments and trainings. So, coming to the objectives of the lecture. So, like I said, we will talk about on the assay development part, what you would do when you first would like to set up a BioCore assay, what are the optimizations that you would like to do, what things like which one to, first of all, how are the, first the assay, how does it, should it look like, then which one can be a ligand, what can be an analyte, what are the different reference surfaces that you can do, and very important also, we talked about regeneration. How do you optimize the regeneration condition, because if your regeneration is not perfect, your runs typically do not go so well, right. So, the first, so let us look at some of the assay formats. The first one is the direct binding assay format, which is very simple. Your interactant is actually immobilized on the surface, like you can see here. So, we talked about in BioCore that you have a ligand and an analyte, right. Whatever goes on the surface is called the ligand, and whatever is flown on the flow cell is called the analyte. So, in the direct binding, your ligand is actually covalently linked to the surface and your analyte is moving on top, right. You also have another direct format, it is nothing, we call it an enhancement, or it is also similar to the capture method, right, what we were talking about. So, the first, the capturing molecule is immobilized, then you actually bind your ligand and then your actual analyte comes and binds, right. So, this is, you can also call this an enhancement molecule sometimes if you are treating this as a direct binding. If this molecule is extremely small, then you can use an enhancer, you know, a specific molecule that it binds to read it. In the direct binding cases, your sensorograms would look something like this. In this type, this is where your baseline is, this is your association phase and this is your dissociation. And if you are looking at, and after that you can actually do a regeneration for this type only. But if you are looking at this enhancement, what you do is actually, first this is where your red molecule is binding to your ligand and then your enhancer is binding. So, that is your final response that you look at, right. There are certain indirect bindings that you can do where we use it, we utilize the competition. So, the binding does not really happen on the surface, you are having the binding happening on the in the solution, right. So, this is called the solution competition. What you do is here you mix the analyte and the detecting molecule in a particular portion. The analyte is kept constant where with increasing concentration of detecting molecule, okay, and you mix them. So, with the increasing concentration of detecting molecule, what will happen is you will, with increasing concentration of detecting molecule, you will have free detecting molecule in the solution, right. And then when you put this mixture here, so with the increasing concentration of analyte, you actually see drop in response unit, right. So, it's actually a reverse, you know, with increasing, usually in the direct binding with the increasing concentration of analyte, you see increase in response unit. Here you are seeing just the opposite, right. This is another one, it is a similar format. So, here you are actually having a competition in the term that you are having a competition in the solution. The bound ones will not come and bind here, only the free detecting molecule are available to come and bind, right. Now, here when you are mixing it with so this is where we call it is a surface competition. The competition is happening at the surface. You have the analyte as well as you attach or link your analyte with a competing analyte, in the sense it's a high molecular weight analog where you link it with, and the key is the high molecular weight analog. When you attach it, the size of this should be considerably larger than your analyte. You mix them. Here they actually, in earlier case the binding was happening in solution, but here of course there is no binding. When you put this mixture on your surface where your ligands are bound, you see the binding only because of your competing analyte. Okay. When you these analytes are so small and negligible, you do not get to see your binding. So, here too, with increasing concentrations of your analyte, you actually see less and less of binding. So, it is again a reverse plot, right. So, if you summarize the response versus analyte concentration in direct binding, you see increase in RU with analyte, whereas in indirect you actually see a decrease in binding with your. So, these are basically two types of. Yes, sir.
So on the direct enhancement, is that, how are you going to get the rate constants on that? Or isn't that dependent on the rate of the enhancing mode of binding, or is that?
That's right. So, you probably will not get the rate constants there. You can only do certain applications like concentration determinations.
Oh, I see.
Yeah, that's a very good point. Yes. So, so these are different various formats that are offered, but then again it is limited to what applications you are using to. Yeah. Okay. Coming to the general steps of Beer assay, I think I don't need to explain that. You are all now quite comfortable with this, you understand this. But we will talk about now in detail on the surface preparation. Why, so surface preparation. So when you have set of two interactomers, right, you would like to use it in beer core to see and bind it, right. So you need to first understand why you would like to, which one you would like to choose as a ligand, which one you would like to choose it as a analyte, things like that. Okay. So first of all, what is immobilization? We all know, right. How do we stick it to the surface? We covalently link it, right. It is not just any attraction, it's covalent linkage, right. So once you immobilize, that is immobilized for good. You cannot strip it out. Okay. So once you immobilize something on the surface, you can't strip it out, right. So points to consider, first when you have it, which one you would like to immobilize, then how you would like to immobilize, which chemistry are you going to use, whether you're going to use the direct binding approach, you are going to use the indirect binding approach, all these things, right. What is the immobilization level you would like to use, okay, because when different applications require different immobilization techniques, amounts, right. So for example, in kinetics, adding too much of ligand is extremely detrimental. You do not get a right kinetic data. Your ligands have to be immobilized very, very low. Whereas if you are doing a concentration analysis, you need to have a high ligand concentration. So these knowledge is very, very important. Okay. And which sensor chip is suitable for your assay? We talked about various sets of sensor chip like CM5, CM3, C1 when you have a lot of non-specificity, hydrophobic for HPA, so all these things, NTA for nickel tagged if you have something like that. Okay. What to immobilize? We come back to the question of which one to immobilize. So the first thing that you would like to look at is actually the molecular weight of the interactant. Which one would you think should go as a ligand? If you have two interactants and one of them is large and one of them is small, which one would you like it to go as a ligand? The small one, absolutely, because you can use the larger one as an analyte, so you get use a higher response. But having said that, with the beer core T200, the sensitivity it offers, even if you have a smaller, small molecules can still be used as an analyte, but you do see some amount of background, a noise, but then it is still enough to do a kinetic analysis, but not with the earlier versions like X100 where the sensitivity was not as high with the T200. Tagging of the interactants. If you have a tag, you would obviously like to use a capture method to put it in as a ligand, right? Functional groups. The few things, functional groups and binding activity of the immobilized, they go together actually, because if you are using a functional group to immobilize which is actually in the active pocket, then you destroy the activity, then then there is no point, right. So you need to have some amount of information of the functional group that you are using, and that is not being used to immobilize it on the surface, right. Purity. The most pure one should go as a ligand. You cannot have an impure ligand. The more junk you immobilize, the data becomes more dirty. You can still use it as an analyte. So of course, again, when I talk about analytes being impure, it's only limited to applications like binding experiments. If you have to do kinetic, you cannot afford to have an impure analyte. But if you are doing a concentration analysis, if you are doing a binding, it's fine to have a slightly impure analyte. Valencies. The more number of valencies, where do you think it should go? It should, so like an antibody and an analyte. So you used anti-beta 2 microglobulin today, right? And beta 2 microglobulin as an analyte. Which one did it go on the ligand? The valency was 2. You put that on the surface, right? So, but if you had done the opposite and Okay, so the question is, if you have an antibody on the surface and have an analyte on the flowing on the surface, it is actually a 1:1 binding, because we call it as the binding is considered with respect to the analyte. But if you have the antibody on the flowing on the thing and your analyte, the same detecting molecule is on your surface, then it becomes bivalent analyte, right, the bivalent analyte. So, your mode would change. Okay. PI of the protein. PI of the protein, I would like to slightly stop by out here, and we will explain it in greater detail in the upcoming slides, because that you will see is an extremely important when you are immobilizing your ligand. Okay. Amount of available, obviously if your amount is very available is very little, then you would rather use it as a ligand, because when you are using it as an analyte, you have to run various number of cycles, leading to more number of requirement of analyte. And then assay requirements. Of course, assay requirement is very, very important. What actually do you want to get out of the result? That is very important too. Surface preparation, I think you saw this slide. You know surface can be prepared in two ways. One, you directly immobilize the ligand, right? In the other one, you actually capture your ligand. So in capture, you are actually capturing molecule is actually immobilized directly on the surface. Now the difference would be is that in this case you lose the directionality of your ligand, like we were discussing. So it is actually immobilized at random using any of the free amine groups or the thiol groups on the surface. Whereas if you are using a capture molecule, you maintain a directionality of your ligand if your assay requires so. This one that you are looking at is actually the step of your immobilization. So how do we immobilize is like first we activate our surface using EDC NHS, and don't ask me what's the full form, because I really cannot remember ever the EDC NHS. What it does, it actually activates your surface into the carboxyl groups into a reactive ester group. Okay, and that's where you're seeing the EDC NHS is being pushed. After that, at this point your surface is actually activated, and then you push your ligand, okay, which has the free amine groups or the free other groups. And at this point, all your proteins are getting covalently attached or linked to the surface. Okay. And then finally, you do a blocking with ethanolamine. This blocking is to block all the activated ester groups which has not formed a covalent link, because if you do not block at that stage, when you are actually passing your analyte, they may come and bind there, right. So this blocking step is extremely important, and the difference from here to here is actually your immobilization level. Okay. Choice of immobilization strategy, it will depend on your ligand. Again, amine coupling is very widely used, in most cases, more than 90% of the cases we typically use amine coupling, particularly in proteins when we are talking about, because there is huge amount of amine groups available in most proteins. Right. So if your ligand is actually unstable, then you would actually use a capture method, right. If you're using a covalent chemistry to immobilize and your ligand loses its activity, then you would rather use a capture method. If it's an impure ligand, like remember we said that your ligand needs to be very, very pure to be put on the covalently linked on the surface. But if it is an impure ligand, then you can do is capture it, right. So you can only capture the your specific ligands. If your covalent linking actually loses the results in loss of activity, say for example you have done amine, then and it loses the activity, then try and use a thiol coupling or aldehyde coupling. For acidic ligands, typically capture chemistry is mostly used, and if regeneration condition is also difficult, like if you have not found out a regeneration condition, sometimes it is very difficult to find out regeneration condition for some cases. In those cases also you use capture chemistry. Okay. Coming to the PI point, which is extremely important here when you are immobilizing your ligand, and I think I don't need to reiterate this, we all know what's the, what happens when your protein is put in a pH less than your pi, your protein is actually positively charged, right? And if it is more than your pi, your protein is actually negatively charged. So when we use this, it's the same thing in a more schematic thing. Now, the pKa of the surface, the chip, the pKa of the surface is actually close to 3.5. Okay, so if you are going less than pH 3.5, so I am talking about a scenario where I would like to immobilize my ligand, and I would like to put my ligand or the protein in a certain buffer where it is in a particular charge, positive or negative, let's decide that, right. So if I put my protein in a pH 3.5, say most likely if the protein, of course pi is higher than that, it will be positively charged, but the surface actually loses its charge. Okay, it has absolutely no charge. So in that case, there is no attraction between the protein and the surface. And why are we talking about the attraction between the protein and the surface? Because we talked about covalent linkage, right? But the covalent linkage to happen, the protein has to come close enough to your surface so that covalent bond can be formed. Okay, so this scenario where your pH is very low, typically it's not a good scenario to immobilize your ligand. You do not see immobilization. So it's too low for immobilization. Now at a pH higher than 3.5, your surface actually attains a net negative charge. Okay, and if your pi is higher than that pH and in that particular pH, and you are able to keep the protein positive, then your attraction happens. Okay, and this is the ideal scenario where your covalent linking can happen very ideally. Again, if your pH is higher than your pi, then there is no attraction because both of them becomes negative. Right? So that's what we call it as pre-concentration also. So when we are doing a ligand immobilization, and sometimes we see that we are not attaining the amount of RU that we are expecting, this is something that is extremely important apart from the chip quality and EDC quality and things like that. So this is also something very important to keep. And this is the same thing that we talked about. Now, not all the time you may have information about the correct PI, right. So we have a tool called scouting, pH scouting, which actually tells you which buffer would be most convenient or ideal to use it for immobilization buffer, okay, for immobilization purpose for that particular protein. So you can take a little bit of your protein before you do your actual immobilization and run into this pH scouting experiment, okay. Take a small amount and then mix it with various buffers. Typically the buffer that we supply is from pH 5.5 to pH 4, okay. Mix them in all different same concentrations but different buffers, and then run them, and then try to compare and see what is the peak like. So remember, here there is no immobilization happening, it is just the pre-concentration, only the attraction that is happening, and then you see the increase in RU out here, right. So in this case that you can see that pH 5.5 is the lowest and the highest is pH 4. So what do you think it means? Does that mean that pH 4 is the best for immobilization? So most people think that increasing the more lower the pH we go, we can attract the protein more and eventually we can get the best. And well, there is some amount of truth in that, but not always. So if you see out here in pH 5.5, which is actually kind of like the highest pH here, you attain quite a large amount of RUs, okay. You go to around something like, I can't even see 10,000 RUs, which is an extremely huge amount of RUs. You don't need that much amount of proteins to, if you are reaching around 4,000 or 3,000, it's more than enough to, do any of your applications that we are talking about. Now, so we actually did not get enough information from there. So we took the same Same thing, and we ran it through the whole immobilization process, right. And you see in pH 5.5, you get to around 13,000 RUs, right, and pH 5 you get to around close or maybe similar. I don't think there's, I mean 13.5 and 12.6, I think I would say it's very close to each other. 4.5, there's a reduction, it's much less, and then again 4, it's even less. So whereas our pre-concentration earlier showed, you know, with 4.5 and 4 it was still increasing, but here actually you are actually attaining a much lesser RU than in, considered to pH 5 and pH 5.5. The logic out here is actually, so when you are actually attracting so much in pH 5.5, increasing the lowering the pH even further and attracting doesn't really help for covalent linkage. So that's where you start getting your steric hindrance and where your, you know, your covalent linkage is not again you know, happening in an ideal scenario. So the key thing, like she said, is to have your proteins in a comfortable environment close to where your proteins will be comfortable, not stress them out in you know, in harsher condition. If required, if you do not see any rise, like for example in these cases, if you do not see any rise in pH 5.5 and 5 and suddenly you see a pH rise in 4.5, that's where you go into a low, you know, lower pH like 4.4, 4.5 or 4. Otherwise, stay close to you know, more comfortable environment. Does it make sense? Okay. Now, I think somebody was asking about the immobilization level. So this is, so how do we find out the immobilization level and in Biacore term, and how much should we immobilize actually when we are doing a Biacore assay? So we have this formula which we call it as it's kind of like a, what do you say, Ved Vakya in Biacore. R max is equal to molecular weight of analyte by molecular weight of ligand multiplied by RL into the stoichiometry. So R max, we haven't talked about R max yet. R max is called the maximum binding capacity of your surface. Once you immobilize your surface, the capacity of the surface to bind maximally your analyte, that's your R max. Okay. RL is the ligand immobilized. Okay. So when you immobilize your ligand, you get a particular RU, right. Say for example, you immobilize 500 RUs or 1000 RUs, right. So that's your RL, and stoichiometry of your binding, whether it's 1:1 or if it's a bivalent, it's 2, right. So typically, theoretical R max, what we did find out from here, is higher than your experimental R max. Usually when you actually immobilize your ligand, you tend to you know, lose some activity, you know, and or your ligand to begin with may not have 100% activity. But in some cases when you see much higher R max, you know, in experimentally as compared to theoretical, immediately it should strike a bell that a bell should ring in your mind that something is wrong. Either the stoichiometry that we considered was not right, or there is some non-specific activity, or there is aggregates happening, right. So there's a small exercise if you would like to do, hopefully it will wake you up if you guys are sleeping. So for say for example, if we have a ligand that I would like to immobilize, and I would like to work at an R max of 100, okay, and the molecular weight of your analyte and ligand are given. So your ligand looks like a map, like 150 kilodalton, your analyte is 25 kDa, stoichiometry is 1, and I would like to reach an R max of 500, right. So how much RL, how much of ligand should I immobilize? Anybody? 600, right. So if you get 600, then typically I would, since your theoretical R max is usually higher than your you know, experimental R max, we typically go ahead, and if it's 600 from your theoretical, I would go ahead and immobilize 700 or 800 to compensate a little bit, and then, you know, start your experiment. Okay. Is it okay?
How do you
Right. Yeah. So, so if you're doing a kinetic analysis, you have to be even 100 RUs is quite high sometimes. Sometimes you have to go as low as 50, 20, or T200 actually allows you to work as low as 5 RUs, Rmax. Okay, so you can still get a very decent, nice, without noise graph, which we can perfectly do an evaluation on and get a KD value of it. If it's a concentration or affinity determination, then it has to be on a higher range. Like when I say higher range, it can be around say 3000 to 5000, ranging on that. So you find out the surface saturation. Say for example, if you are immobilizing a 150 kDa molecule, so your surface saturation comes at close to around 10,000 to 15,000 RUs. Okay, that's the surface saturation. Yeah, roughly. And if it is say around 25 kDa, then it is around 2000 or 2500. That's the surface saturation. And when you're doing a kinetics, you should never be in a saturation mode. There is something called mass transport limitation that happens, which actually affects your concentration of your analyte. So you would have to keep your ligand concentration extremely low. So otherwise you get erroneous kinetic results.
I'm a bit confused. When you say 600, 700, what's the unit?
RUs, resonance unit, response unit.
Intensity.
Yes, exactly. So like I said, right, it is related to the refractive index. So the change in the change in mass will change the refractive index, and that is related to your response unit. Response unit.
Because the analyte molecular weight is not given, so we have two unknowns in that.
No, analyte molecular weight is there.
Okay, there is.
Yeah. Okay.
What's the maximum Rmax that T200 allows?
Well, it can allow a lot. I mean, and then it's not about T200 allowing it. It's the analyte and the ligand molecular weight which will contribute to it. Yes.
First is 5, you said.
5 RUs of Rmax. Yes.
Okay, so I am sure this was a very informative lecture by Dr. Uma. You are convinced that she is able to convey the very hard ideas and principles involved in this technology in a very lucid manner. In the next class, Dr. Uma will continue to explain some more detail of Bayer core technology. She will also provide a demonstration and working of how to do SPR experiment on Bayer core platform in the next class. Thank you.